And he's then looked at what the order of events is when you have flow. So if we have discharge here in 2005, the stream channel was dry, and then in late April, it started flowing, and then by it actually dried again about April after that. And we see the very first things, algae come on really quickly. Fish are able to move in, so we've got this sort of cycle where the fish are down by the nature trail, and then when the streams start flowing, they start working their way up the stream channel. And then the crayfish come out of the banks and they're able to reproduce, and their populations come up. The macrovertebrates, the adults, are able to fly in and lay their eggs, and the larvae can develop. Water striders are in right away. And then the flow goes down to essentially zero, and the raccoons eat all the fish. And then the next year, that all starts again. So one of the ideas is that if you have global climate change, you're going to change the intensity and frequency of this. And it turns out when the fish and the invertebrates are there, it changes the ecosystem range and its trajectory. So you're changing the trajectory in the way that the system works if you have more frequent flows. And so these are some of the players. I should put this up first. The darters, the stone rollers, which is the grazing minnow, the possum, and the crayfish. There's two orchidectes species out there. They're the major things that alter the ecosystem structure. And also, if you stick a net out down there, the things you're most likely to catch. So one of the problems with doing experiments like that is they get blown out by floods, or you don't get water when you want it. And so we have also an experimental stream facility out there, and this is what Keith Giddo's put together, and then we've drummed up money from various sources to build it up from 12, where we started, to 36 units. And each of these units has a little motor in it, and they can be separated, or they can be put together in a chain. So we can have water flowing in a circle inside of these things, recirculating and simulating the stream. And you can do 36 different experimental treatments. Then you can control when the flood and the drought happen. You're not going to Mother Nature there. Or if you want, you could do 6 beautiful pool combinations of 6 together, and then you have 6 goes up to 36. Or you could actually chain all 36 together in one big long stream thing. And you put fish in them. If you want to alter the community, Eric and Martin's been doing a lot of this, much different things over it. There's these viewportals on the side. So this is basically simulating a flood, where you've got the algae going in, and you pull the plug, and you shoot it with a high pressure washer hose, and you've got a trolling motor in there to kind of get things going as you do it, and you refill it when it's clean. They named this pressure hose Walter, and I'm not but in these, we found that the fish alter how the streams recover from flood and drought. We found that the consumers really do have an effect on the way the ecosystems do, by extension, water quality. And the other thing that we've done is we've crossed the fish with nutrient additions. We found that nutrient pollution has a huge effect on how these systems recover from flood and drought. So the nutrients have nutrient pollution can have a big effect on these ecosystems. So I'm just going to talk about what we're sort of developing. You might see some of these experiments. We did our first set of experiments this summer down below the Nature Trail Bridge. We don't get any flow. We might not do them this spring. We're scheduled to do them this spring. And this is a cross-continent experiment on scaling consumer and loading ecosystem rates. And we're doing it at Konza and Puerto Rico, North Carolina, and 2 Alaska sites. And when we do experiments, the easiest thing to do is say, okay, let's grab a handful of this stuff, right, and measure the rate on it, and then that's what the rate is in full stream. But the question is, can we really scale up that way, scientifically? And And we don't want to know the answer to that probably because it's the easiest way to do it, is to do this. So the way the experiment's set up is we have consumer exclusions in those fences like I showed you, small scale in little baskets. And then we're taking whole reaches, maybe a couple 100 meters or so, putting fences on the top and the bottom of them, and we have methods that we can measure the ecosystem rates in the entire reach, and then we can go and shock out all the fish and move them out, or shock them and put them back in as control. And the question is, if we take those baskets and we sum it up, does it equal the whole stream? And then the next scale is, well, what about the reach? If we take that 100 meters, can we scale that up to the whole watershed? And so to check that, we'll have 20 synoptic sites where we go around and measure everything, and then the modelers say, okay, we'll take what's going on in the reach and we'll predict what should be happening in the whole watershed. And check that by sampling. There are predictions by sampling. If it doesn't match, then what do you have to change in the models? What are we missing when it comes to scaling up? So what we're trying to do is get up to the scales that people interact with the environment. We care what happens at watershed levels. When we talk about nutrient pollution downstream, that's what we're concerned about. It's also the scales at which organisms operate and evolve, right? They're not one little thing. They disperse through an entire watershed. So it's also relevant for basic ecology as well. So our first experiment starts in Puerto Rico, and I'll go down there at the end of the month.
Do you need
You pay your way. And then the other thing that's happening here, you may have caught a little bit of wind of, is NEON, National Ecological Observatory Network. And that will consist of 30 years of observation, of detailed instrumentation, and also sampling. And the terrestrial site, the tower for the terrestrial site, will be up on the top of K2. And that's right sort of where it's near what was K20 and the nature trail. I think it's going to have to be rerouted a little bit to get around the edge of that. And then there'll be another one down in that crop land that we passed just as we came in. Those will be the terrestrial site. The aquatic site, though, we also have an aquatic site, and they're going to put that in just down from where the Columbia building is, just right over there down Kings Creek. In addition, they have what they call relocatable sites. Relocatable sites are going to be down just on McDowell Creek, and that will be there, they say, for 5 or 10 years. My guess is they'll just put them in the fall 30 years too. And that's just off that ag farm there. You get down to McDowell Creek from there. In addition to this, we'll include a 10-year experiment on nutrients and animal effects on the ecosystem. And so essentially when you do these manipulations, when you do, say, a fertilization experiment, you usually just throw some stuff in and see what happens in a couple of weeks. And so one of the questions is, can you take a couple of weeks and extrapolate what will happen relative to something like putting a cropland where you put nutrient in year after year after year? We don't know that. We've never done the experiments there's 2 experiments of those long-term fertilizations. One's been done in North Carolina. One's been done up here near Tulip Lake. And both experiments, the long-term effects are quite different. You get these surprises that come out that you didn't expect based on the short term. So we'll have this nutrient enrichment experiment, and then embedded in that we'll have consumer manipulations. In these cases, they'll keep consumers out of smaller areas with electric fences, and that'll be going on down the stream. So that they should start building that out within 2 years from now. So when you see that, you expect to see that. It's a nice thing for Konza because all the support comes in from the NSF, and it's funded through a major research infrastructure program where it's the thing they use to fund telescope arrays, super colliders, ocean-going vessels, things that are really expensive big projects. And this is the first time that the ecologists have gotten this kind of thing. So it's a big deal for environmental research to have tapped into this and to be recognized as needing that level of research instead of just being a little old professor like me working in my own institution, right? That a whole network is important to do that. So we'll see that develop over the next couple of years. So in conclusion, intermittent streams are important. They are very endangered. Remember, you all hear the things of 5% of the tallgrass prairies left, correct? Well, you know, many of the patches of tallgrass prairie that are left, except in the Flint Hills, are small, too small to encompass